Good morning, students. Today we're going to do consequence analysis. I'll be focusing on pool fire and jet fire. So consequent analysis is part of a risk assessment that determines the degree of damage that will be attained due to the occurrence of a hazardous event. So the outcomes of consequent analysis will actually give us information on all possible occurrence of unwanted deviations from a process, how to overcome the occurrence of the unwanted event, how to prevent or minimize the consequence of a hazardous event occurrence, and the state of affair to the workers and surrounding population if there is any occurrence of an hazardous event. So how do we decide which consequent models to use? So consequent analysis is usually done by a professional technologist who has an experience in the actual problem that can occur in a plant. And following is a logic diagram which shows the decision-making process when undertaking a consequence analysis. Okay, so this is an overall diagram. So if we have an hazardous substance, which route should we take to analyze the possible consequence or the outcome? So if you notice, there's few layers to it. The first layer is the source model. So we learned source model in the previous chapter. So first layer is the source, whether is it from a pressurized leak, or is it from unpressurized leak, or is it from other incidents, and then the phase of the leak, okay, such as this, and then whether this leak will cause dispersion, any dispersion to the surrounding. And from there, what is the possible events that can occur? So these are the events that can occur, like jet fire, flash fire, fireball, VCE, pool fire, and BLEVE. So all these will actually give us thermal effect. Okay, so we can calculate the thermal effect of these events. If there is any heavy dispersion of vapor, and if it is toxic, so we can also calculate the toxic effect. So we have seen this in the toxicology chapter. And if there is any explosions which causes external fire, so that will cause a BLEVE, and there will be explosive effects. Part of this has been covered in the flammability chapter. Okay, so from these effects, we can identify the outcomes, the consequence of these events. Okay, the following slides explains what I have just mentioned from the chart. So the first level is the source model, which gives us the release conditions, rate of discharge of hazardous materials, release duration, and size of the liquid pool formed for the liquid phase discharge. So we saw this in the source model chapter. Then we will need a dispersion model. So we'll be looking into this in our next chapter on toxic dispersion. And then we have the event model, which gives us either the fire event or the explosive event. So this consequence analysis uses mathematical models to calculate the discharge rate, the fraction of vapor and liquid, the size of the liquid pool formed, and then the concentration of the release. So why do we need this? We can use this information to calculate the degree of harm to human beings who are exposed to the material, be it in a liquid form, which gives a thermal effect, as well as the toxic effect, and at some cases explosive effects. Okay, so the degree of harm can be fire or explosive or toxic. So this consequent analysis models can give us the probability or chance of an individual is injured or will die from the unwanted event, or the number of people that will be exposed to the harmful effects. So how do we get this? Is by using the probit table. So we calculate the impact and we use the probit equation and probit analysis to identify the degree of impact on the people and the surrounding. The consequent analysis models can also give us information on the possible loss in terms of monetary values and the amount of money that we need to set aside for compensation, both for people as well as for the building. Okay, so this is why we need consequent analysis models, and it is part of risk assessment. So this consequence modeling, although we are learning the part of the theory in our class here, but in real time or in the industries, it can actually be done using softwares. So when we provide some necessary informations, there are softwares that can actually calculate the consequence model for us. Okay, for our class today, we will look into fire and thermal radiation modeling, focusing on pool fire and jet fire. So the jet fire, fireball and bluey has about this similar kind of equations used in the modeling. So don't be afraid when there are too many equations. Okay, I'm going to show you quite a lot of equations. The slides after this are going to be a lot of equations. But the whole idea is to let you know what are the factors that we need to take into consideration when we do consequent modeling for these events, and what are the equations that is present. Okay, so later I will also explain how we use the equations. So take it easy and just learn freely. A pool fire occurs when a flammable liquid is released from a containment and forms a pool, which eventually found a source of ignition. So we learnt in flammability, so if all the three components are present in sufficient amount, then the ignition will take place. The flame will take place. Okay, so the size of the pool formed is very much dependent on the situation when the release occurred. So whether the released area is constrained by a bund wall or a dike. Okay, so this is a pool from a tank. So when leak occurs, so the liquid will start to build up. So this is a bund wall. So you have a wall against it to stop any leaking, or you can have a dike. Okay, so the conditions may differ for both types of area. Okay, so this is an example of a pool fire. So if you notice the flame, this is a flame, this is a fire, and then there's a direction to it, so it's affected by the wind direction. Then you also have plumes forming at a certain direction. Okay, so for pool fire models, the mathematical models to characterize a pool fire are this. So we need to know the combustion rate of the material, the pool size, flame geometry, which includes the height, inclination, and drag of the flame. Then emissive power from the surface of the fire, geometrical view factor based on the recipient of the heat, that means in which direction there are either environment or people, so from which direction are we looking at the fire, so that affects the impact or consequence of a pool fire. atmospheric transmissivity. That means for that, at that point of time, so what is the atmospheric condition? So how does it aid in the transmission of the fire? And the heat flux received by a target at a specified distance from the fire. So this is mainly required for us to let's say there is an event of fire occurring, so where should our collection point be so we are not affected by the heat flux? So we would need this information. The following slides will give us the equations for the characterization. So this one is for combustion rate. So the combustion rate of a liquid increases with the increase of pool diameter, because obviously there will be more carbon source when the diameter is bigger and is spread out. So the rate will be faster. So a constant combustion rate is expected if the pool diameter exceeds 1 meter. So exceeding 1 meter, so we expect it to be constant. So this is the equation to calculate combustion rate, so which is self-explanatory. It's given down here. And then we have heat vaporization. So we have modified heat vaporization. So how much heat will be emitted by this pool. Then mass burning rate. So how much of mass that is present, and so what is, at which rate is it burning, how much. Okay. Then we have, so if the density data of the density of the burning liquid is not known, then we can also use this equation. So these are values and constants which can be found in literatures such as this. So some of quite a lot of materials, the burning rate has been defined. Okay. And then the pool size. So although the pool size are constrained by a bund or a dike or drainage, we still, and it may not be circular, but for thermal radiation modeling, we still assume the pool to be circular. So this is the equation for us to calculate the size of the pool. Then we have equation 5, which is used to calculate the flame height. Okay. So this is equation 6 is also flame height, but this is an experimentally developed equation when using natural gas at a large scale basis. So if we have an incident which involves a natural gas, so we can use this equation instead of the general equation. So this is the general equation. So this is the equation for natural gas. Okay. So this explains the terms, the parameters. Then we have fire inclination and drag. So as we seen in the picture just now, the fire was inclined towards a direction, towards the left direction. So this happens due to wind blowing across the fire. So if the velocity of the wind is high enough, the base of the pool can also be dragged downwind. Okay, so we don't want that to happen. So we can also calculate that based on the atmospheric condition. Okay, so this is the equation to determine the angle of inclination of a flame. Right. Okay. Next, to determine the heat flux from a pool fire, the existing equation is very much dependent on the flame temperature, and it's very difficult to determine a flame temperature. So therefore, we have two different approaches that can be used to estimate a heat flux from a pool fire. it can be a point source model or solid plume radiation model. So the point source model is based on the total release of the combustion energy. So this is at the source of the fire. So the solid plume radiation model uses the thermal heat flux measured from the experiment. So this plume radiation uses the radiation, the heat flux from the plume, the flame. So this will also include the absorption of heat by the smoke of the fire. So this is the flame part, including the smoke or the soot part. Okay, so that is solid plume radiation model. So for point source model, we have a direct equation. So we just calculate the total power of combustion, okay, using this equation. Okay, then this explains the terms in the equation. And then we multiply the QT, the total rate of energy generation from combustion that we calculated in equation 9 in this slide here. This is equation 9. We multiply it to obtain the amount of energy that is radiated. So QR is the radiant energy from the combustion of the fire in the event. The QT is the total energy. N is the fraction of energy from combustion converted to heat radiation. So this is a coefficient that we have to determine. So the typical value is between 0.15 to 0.4. So this N values has already been studied for quite a lot of materials. Okay, so it is usually present in the literature. So we can use the literature to get the N value. Okay, so that's using point source model. Then we have solid plume model. So instead, assume that all the flame volume that can observe emit the heat radiation. So whatever you see, the flame part that you see will emit heat radiation, and the ones that you cannot see and you cannot feel, we assume there is no radiation from it. Okay, so the problem with this approach is that for heavy hydrocarbons, there will be a lot of soot produced in the smoke that prevents emission of heat radiation from the flame. Okay, so in actual fact, heavy hydrocarbons will actually have lesser heat radiation than what is calculated in the model, because the heavy hydrocarbon soot will actually prevent the heat radiation because it's too much of carbon. Okay, so when there's too much of carbon, the fire cannot occur. Okay, so this is the equation for solid plume model. So it takes into account fires that produce a lot of black soot for hydrocarbons with high molecular weights. Okay, so let's see what does EAV is the average emissivity power, EM is the maximum heat emission power, and ES is from the smoke. So it takes into consideration the smoke and also the experimental parameter and the pool diameter. So this experimental parameter for a particular hydrocarbon. When we use equation 11 for gasoline and kerosene fires in an experiment where there is black smokes, the equation 11 produces a heat radiation emissive power of 56 kilowatt per meter square for a 10 meter diameter pool fire. And when the pool diameter of the pool becomes bigger, 10 times bigger, there is a decrease in the heat radiation. Okay, so it's a direct function to the diameter of the pool. The fire involving propane, ethane, LNG or other light gases, black smoke do not occur with the flames. So for these events, equation 11 cannot be used. The point source model is more appropriate to be used for light gases. Okay, the next characteristics of pool fire is geometrical view factor. So the value of the heat flux received, that means the heat that we can feel by a target or by a person around it, is dependent on the distance from the surface of the fire. So the further the distance from the surface of the fire, obviously the lesser the value of the heat flux. The reduction effect of the radiation heat flux with distance is taken into account as a view factor. So for a point source model, the view factor is determined by this equation. So this x is the distance from the point source to the target. So we always go back to the point source. So for example, if we have a fire, right? So we have a fire, and this is where the source is, right? So let's say this is a plane. So if let's say this is where someone is standing, okay? So someone is standing here. So the x is always from the source. Regardless where you are standing, the x is always from the source. Okay, so this is point source model. Okay, so equation 12 assumes that all the radiation is being emitted from one source at a point, and the target object is directly in line with the source. Okay, so it's only applied to the heat radiated, not the heat flux. Then for the solid plume model, the view factor can be obtained for flames with no inclination. You can obtain from figure 10, and for flames with inclination we get from figure 11. So no inclination means, let me show you. So this is no inclination, so it's vertically upright. If there's inclination, then there is a wind effect. Okay, right, so this is the tables, the graphs that can be used to identify a view factor. So if we know a distance from flame axis to the ratio of the pool radius, so this is height to radius, so we can identify the view factor. So this is for vertical fire. Figure 10 is for vertical fire. Then figure 11 is for inclined fire. Okay. So if you notice, the figure 10 requires the ratio between the flame height and the diameter of the pool. But figure 11 requires an additional factor, which is an estimation of the angle of inclination. So we need angle of inclination. Right, so near to the fire, when you're very near to the fire, the view factor do not depend on the flame height, because the target is exposed to the maximum radiation. So for a heat flux at the target, for this is the next characteristics, heat flux at the target. Just now it was view factor. So if the point source model is used, the heat flux received by a target is explained by the equation given. To calculate a heat flux at a target for a point source model, so we use this equation. So this is the input from the geometrical view factor. Then we also have elements of atmospheric transmissivity. Okay, tau A is atmospheric transmissivity factor. So it is governed by this equation, where we need the partial pressure of water and the difference between surface of fire and the target. So that gives us the atmospheric transmissivity. For the solid plume radiation, so the equation is slightly different, where the view factor, we get information from figure 10 or figure 11. Okay, so it's F21. Okay, so this gives the information about heat flux at a target floor if we use the solid plume model. So let's see figure 12, which gives us a logic diagram on how to determine the effect of a pool fire. So this is to summarize the lecture for this slide. So if we have a pool fire, first we need to estimate the vertical or mass burning rate. So these are the equations that we use. And then we estimate the maximum pool diameter using equation 4. Then estimate the flame height using equation 5 or 6. And then you have radiation, then you have to choose the radiation model. So for light hydrocarbons, we use point source radiation model. For heavier ones, we can use solid plume radiation model, and we estimate the thermal effects. So how do we estimate the thermal effects? So for point source model, we need to know the radiation fraction, location point, view factor, transmissivity factor, and finally the heat flux. And for solid plume radiation, we find the surface emissivity power, and then view factor, transmittive factor, and then the heat flux. So this is the conclusion. So this is what conclusion of this lecture, and this is what I expect you to know: the characteristics, the models or submodels that is required to model a pool fire. Right. And the next slides will discuss jet fire. Thank you.